Have you ever just looked up at the night sky and felt small? And you start to wonder, how big is all of this? I mean, how on earth do you measure something so mind-bogglingly huge you can't ever hope to touch its edges? Well, that's exactly what we're going to dive into. We're going to climb the ladder of cosmic measurement, one rung at a time, to try and get a handle on that very question.
I mean, it's a real head-scratcher, right? You can't exactly stretch it tape measure from here to the next star. You couldn't even send a probe there in 100 lifetimes. So astronomers had to get ridiculously clever. They had to invent this whole cosmic toolkit just to start mapping the heavens. So where do you start?
Well, you start with the fastest thing there is, light. It just zips along at an unbelievable 300,000 kilometers every single second. It sounds like the perfect ruler, doesn't it? Okay, let's put it to the test and see how it holds up. To get to our closest celestial neighbor, the moon, light takes just over a second. 1.3 seconds, boom, you're there. Okay, that feels pretty manageable, almost instant. What about Mars, our planetary neighbor? A beam of light makes that trip in about 3 minutes. Again, we can still wrap our heads around that. It's like a short coffee break. But let's take a real jump. To cross our own galaxy, the Milky Way, from one side to the other, it would take a single particle of light 200,000 years. Whoa. All of a sudden, our fastest thing in the universe yardstick feels kind of tiny. We are definitely going to need a new tool. And that brings us to the very first step on what astronomers like to call the cosmic distance ladder. To measure the stars in our own backyard, we use a trick that's, believe it or not, surprisingly simple. It's a cool little trick called parallax. You can do it right now. Hold your thumb out in front of you. Now close your left eye. Now switch, close your right eye. See that? Your thumb looks like it's jumping back and forth against the background. Well, astronomers do the exact same thing, but instead of blinking, they use the Earth's orbit around the sun as their two eyes. By measuring that teeny tiny shift against the backdrop of really distant stars, you can basically draw a giant triangle out in space and use simple high school trigonometry to figure out the distance. And you have to remember this. Parallax is the only direct way we have to measure stars. Every other method we're going to talk about is built on top of this one. It's the foundation for everything. But here's the catch, and it's a big one. That shift is infinitesimally small. For even the closest stars, it's like trying to see a dime from over a mile away. So yeah, this method has its limits. Big time. And you can see right here just how much technology has blown those limits away. From the ground, stuck under our blurry atmosphere, we could measure out to about 100 parsecs. And a parsec, by the way, is just another huge unit of distance, about 3.26 light years. But then we sent up space telescopes like Hipparches, and now the incredible Gaia satellite. They've extended our reach by 1,000 times, letting us build a 3D map of a massive chunk of our galaxy. Okay, so that's great for our neighborhood, but what about other galaxies? We're talking millions of light years away. At those distances, parallax is completely useless. The shift is just too small to even detect. For the next rung on the ladder, we need something different. We need to find some cosmic lighthouses. The whole idea behind this is actually pretty simple. Think about it. A dim light, well, it could be a weak light bulb right in front of your face, or it could be a super powerful streetlight way down the road. If you only know how bright it looks, its apparent brightness, you have no idea how far away it is. But what if you knew its actual brightness? Then you could do the math. And this is where it gets really brilliant. Astronomers came up with this concept of a standard candle. These are objects out there in the cosmos that have a known, predictable, absolute brightness. They are the absolute key to unlocking the rest of the universe. And lucky for us, astronomers have found two incredibly reliable kinds of these cosmic lighthouses. On the left, you're looking at Cepheid variable stars. They're amazing. They actually pulse. And on the right, you're seeing a Type 1a supernova, which is a kind of exploding star that is just unbelievably bright. Both of these are fantastic standard candles. So Cepheids are incredible. They have this rhythm, they pulse, and the faster they pulse, the brighter they truly are. It's a built-in instruction manual. We can use them to measure distances up to about 100 million light years. But Type 1a supernovae, get this. They're what happens when a certain kind of star dies, and they always explode with the same exact insane level of brightness. They're so bright, we can use them to measure distances of 1 billion light years, or even more. 1 billion light years. That's just staggering. But the universe is bigger still. For the final, top rung of the ladder,
We need something that uses the fabric of the universe itself as our measuring stick.
So, back in the 1920s, an astronomer named Edwin Hubble noticed something really weird. He was looking at the light from distant galaxies, and as you can see when you compare these two signatures, the patterns in the light, they were stretched out. They were all shifted toward the red end of the spectrum.
This phenomenon is called cosmological redshift. It happens because space itself, the actual fabric of the universe, is expanding. So as light travels for billions of years across the cosmos, the space it's moving through literally stretches, and it stretches the light wave right along with it. And here's the punchline: the farther away a galaxy is, the more its light gets stretched. It's a cosmic speedometer that's also a ruler. So just by measuring this redshift, we can calculate these immense, almost unimaginable distances. And in 2013, a team of astronomers was mapping out these things called gamma ray bursts, and they found a huge cluster of them that all had a similar redshift. That pointed to something impossibly large. What they found is now called the Hercules Corona Borealis Great Wall. It's a colossal cosmic structure, a string of galaxies that is an estimated 10 billion light-years across. To put that in perspective, that's more than a tenth of the entire observable universe. This thing is so huge, it actually challenges our understanding of how the universe is supposed to be structured. Wow, so after zooming out to the very, very edge of what we can even comprehend, let's use this newfound sense of scale to do one last thing. Let's turn the camera around and look back home. Back in 1990, the Voyager 1 spacecraft was way out at the edge of our solar system, and it did just that. It turned around. From 6 billion kilometers away, this is what it saw. This is Earth. Just a single, tiny, pale blue pixel hanging in a sunbeam. The great astronomer Carl Sagan, who fought to have this picture taken, put it perfectly. He said, "Look again at that dot. That's here. That's home. That's us." He reminded us that every person you've ever loved, every idea you've ever had, everything in all of human history happened right there, on that little mote of dust. So in the end, all these cosmic measurements, from that tiny parallax shift to those brilliant standard candles to the stretching of light across billions of years, they do so much more than just tell us how far. They give us perspective. They map our place in the cosmos, and in doing that, they kind of force us to look back at that pale blue dot and ask ourselves, what does it really mean to be home?